So in this video, we're going to simplify radicals. We're going to review over some perfect square roots. We're going to simplify some non-perfect square roots, and we will review perfect cubes, and we will simplify some non-perfect cube roots. First of all, let's review over the perfect square roots. So if we have 1 squared, we have 1 times 1, which is 1. 2 squared, 2 times 2 is 4. 3 squared, 3 times 3 is 9, and so forth up to 12 squared, which is 144. So let's look at the perfect square root of 81. So we're going to rewrite this first of all. We're going to rewrite this as the square of 9. So we're going to rewrite this as 9 squared. And we're going to do a little bit of a review here. So if you remember, this is your radical symbol. This under the radical is called the radicand, so the 81 or the 9 squared. And then the index out here, if you do not see 1, is assumed to be 2 because we're doing square roots. But I'm going to go ahead and put that little 2 there for just the moment. So the square, anytime you have a radical and you have an exponent that is the same as the index, those will cancel out and we're left with 9. So that is one way to solve a square root that is a perfect square here on this case. Or we can just look at this. 9 squared is 81. Well, the inverse of squaring a number is taking the square root. So therefore, we would also get 9 when we evaluated that out. So we have 9. Okay, so let's look at 144. So once again, I'm going to rewrite it. We know it's a perfect square up here because it's in red. It is 12 squared, so I'm going to rewrite that under the radical as 12 squared, just so we'll get used to doing this. Index again is 2. Those will cancel out, and I'm left with 12. Okay, again, if we know that 12 squared is 144, squaring a number and taking the square root are inverse, so we should also get 12 that way. Okay, now let's look at one that is a fraction under the radical. So there's a couple of different, there's a rule here that we're going to apply, and it's called the quotient rule. So let's look at that first. That's this down here. Okay, this is called the quotient rule of radicals. And all it states is that if I have a radical that has a fraction underneath it, I can separate that radical out so that we have a radical in the numerator and a radical in the denominator. So we give both these little guys their own little radical. So let's look and see. Now we're going to do that. So we took the square root of 16 and then we took the square root of 49. So we just separated out our numerator and our denominator. Then we're going to look and see if either one of those are perfect squares. So we look up here. Well, 16 is one of our perfect squares and so is 49. So if we want to just evaluate that out, the square root of 16 is going to be 4, and the square root of 49 is going to be 7. Now, what happens if we get a number that is not in red up here? So the square root of 24, well, we have the square root of 25, we have the square root of 16, but we don't have the square root of 24 there. So we need to use a rule here that we're going to solve this and write it in radical form. Now, I know you could put a square root of 24 into your calculator, but you're going to come up with a decimal number, and we don't want that. We want it in radical form. Excuse me there. So now we have non-perfect square roots. So number one, we're going to look at number one here. So to find the largest perfect square that the radicand is divisible by. And then we're going to break that radical down using that number. So what does that look like? So let's look at 24. So we're going to go lower than 25 and we're going to say, well, 24, is it divisible by 16? Well, we get a whole number. We do not. It is not a factor. We're going to take and divide 24 by 9. That does not come out evenly either. There's nothing that multiplies by 9 to give us 24. So we're going to go down to 4. 4 divided into 24 is 6. So I can break 24 down into 4 times 6, 4 being one of the perfect squares that I have here. Now we're going to look at another rule like the quotient rule we looked at a while ago. We also have what's called the product rule, which just states that if I have two numbers multiplied together under the radical, I can separate those out and give them each one their own radical. So let's do that. We're going to separate the 4 and the 6 out, give them their own radical, and now we'll evaluate each one of them separately. So the square root of 4 here is a perfect square, so it's going to evaluate out to just 2. Okay, now what are we going to do with the 6? Well, let's look at those rules again. So rule set number 2 said take the square root of the perfect square and take it out of the radical. That was the 4 that would come out from under the radical as 2. The leftovers, though, we're going to leave under the radical symbol. So the 6 is not a perfect square, so I have to leave it under the radical. So I get the square root of 4 comes out to be 2. That comes out as 6 because I can't do anything with that. Let's try another one. Oh, another fraction. All right, so let's use that rule of quotients. Let's separate those out first. Okay, and then whenever we do that, we're going to look at what we have on the top, 175. Well, we only go 144 at 12 squared. If you do 13 squared, you're only going to come up to 169, real close to 175. So you would start taking 175 and going backwards on our scale up here and seeing if each one of these numbers would divide evenly into 175. And we would do the same thing with 9, but we can also see that 9 is going to be one of our perfect squares. So that's going to come out from under the radical. So let's just worry about the 175 on top first, because we know it is not a perfect square. So let's see, what two numbers are going to multiply together to give me 175 and one of those being a perfect square? Well, if you kept on going, you would have found that 25 times 7 is going to give me 175. And this actually should have had its own radical down here, and this should have had its own radical up here. Mistake made. So anyway, so now we're going to go back to that rule, and we're going to give the 25 and a 7 and the 9, all three their own little radical. Now we're going to look and see which one of these we can take out from under the radical, which are perfect squares, and which one has to stay under the radical. So 25 is a perfect square, so that's going to give me 5. 7 is not a perfect square, so that's going to stay under the radical. 9 is a perfect square, so I can evaluate that as 3. So when we get through with all that, we end up with 5 times the square root of 7 over 3. Now let's look at cubes. So we're going to just list the first 10 perfect cubes. So if you remember a cube, you multiply the number by itself 3 times. So 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 2 times 2 is 4 times 2 is 8. 3 times 3 is 9 times 3 is 27, and so forth up to 10 cubed, which would be 1,000. So we're going to look at some perfect cubes. We know this is a perfect cube because we have our chart up here. We can look up here again, and I'm going to rewrite this one again as 9 cubed, okay, because 9 times 9 times 9 is going to give me 729. And since I'm doing the cubed root, notice our index and our exponents cancel out, and we're going to be left with 9, okay? Again, you can put that into your calculator. You're going to come up with 9. Or again, 9 cubed, cubing that number is the same thing as is the inverse of taking the cube of that number. So cube root of 729 is 9. One last one. We have 27. So what number will multiply by itself 3 times to give me 27? Well, 27 is 3 times 3 times 3. Again, I'm just going to write it like this. We've got the cube root of 3 to the third. Our index, our exponent is going to cancel out, and we're going to be left with 3. Or we can just look at 3 cubed is the inverse of taking the cube root of 27, which is going to give us 3. Now, what happens if we have non-perfect cube roots? Well, we're going to follow the same rule as we did with simplifying the square roots, those 3 rules. So we're going to look, first of all, to see if we have a number that is divisible by our cube root here. and that is going to be a perfect cube. So I'm going to start here. I'm going to go less than 64. I'm going to go to 27, and I would divide 40 by 27 and see if it comes out evenly. Well, it does not. So then I'm going to go down to 8. Well, we know 8 times 5 is 40, so we can break that down into 8 times 5. Once again, we're going to give them their own little radical sign. Now I see that I do have a cube root of 8, which is going to give me 2. 5 is not up here in the red number, so I can't do anything with it. So it's going to stay in that form. So there it's wrote out like that. So we'd have 2 times the cube root of 5. One last problem, 320. So we're up here at 216. We're going to start with 216, going less than 320. We would take 320 divided by 216, wouldn't go. We would try 320 by 125, we won't go. So we keep going until we found the number that 320 is divisible by, and that happens to be 64. 64 times 5 will give me 320. I'm going to give each one of the little guys their own little radical. And then now I can take the cube root of 64 because it is a perfect cube. That's going to give me 4. 5 is not a perfect cube, so I can't do anything with it. It's going to stay under the radical. And that's how you do simplify radicals.